Well, our next main topic in differential equations will be systems of linear differential equations. We'll frequently have a variable x and a variable y, or maybe even x, y, and z, and they will all be functions of time. T will be the independent variable. So if you remember your linear algebra, that's going to come in handy because we're going to be doing a lot of matrices. So this short video, we're just going to look at some terminology. Matrix notation. The homogeneous system, here we have dx dt and dy dt, and each one of them is a function of x and y. And we would write that using matrices as x prime is going to represent x prime and y prime, little x prime and little y prime. And then we would have the coefficient matrix of the right-hand side, 11, 2, 4, negative 1. Times x. Where, and let me write this down, where x prime is this column matrix. This x prime is the same as dx dt. This y prime is the same as dy dt. And x is just x, y. That's what we're looking for. We want to find out what x is. Now, this is homogeneous because if we were to put everything on one side, we could have on the left-hand side the functions of x and y and all the derivatives, and the right-hand side would be 0. So this is a homogeneous equation. Again, we could write it if we wanted to as the top equation could be written x prime minus 11x plus 2y equals 0, and the bottom one could be y prime minus 4x plus y equals 0. So this linear system is homogeneous. We do not have an independent function of t on the right-hand side here. Here's a non-homogeneous case. We've got three equations, three differential equations with three variables, x, y, and z. And this could be written as x prime, and we run out of room here. This is x prime. X prime is a column matrix, dx dt, dy dt, dz dt, or little x prime, little y prime, little z prime. And then we'll need the coefficient matrix, which the coefficient matrix is going to come from here and here. It's not going to include these extra functions of t at the end. So I'm going to get a 1, 2, 3. Second row, negative 2, 1, negative 5. Third row, 3, negative 1, negative 3. Times x. That gives us this 3 by 3, these 3 by 3 entries right here. But now we have to add the functions of t, which I'm going to write, for now I'll just write it as 4t, t, and negative t. So what I just wrote in blue is the proper way to write this using matrix notation. So as usual, and I kind of ran out of room, maybe I can write some over here. I can do it under here. X prime is x prime, y prime, z prime. That little column matrix, and as usual, x is little x, little y, little z. And we sometimes refer to the coefficient matrix, this. Actually, we almost always refer to that as a capital A. We don't have to. So this would be capital A. And this one over here we might think of as capital F. that matrix. And actually, if you want to, you could put f of t, because it's going to be, each one of the entries will be a function of t. So we could say something like x prime equals a x plus f. I like the looks of this better than, you can say this matrix A is a function of, actually not the matrix A, the matrix F, A times x plus f of t. Let's see, what else? Well, x and y are functions of t, and z. So I could have put an a of t here if I wanted to, and an f of t, but I don't generally do that. I like the looks of just the matrix equation. And then finally, we have a theorem that makes things nice. The solution exists when the functions are nice. Specifically, if all of the entries of the matrix A and the matrix F, A of t and f of t, are continuous functions on an interval I, it could be open or closed interval, then there is a unique solution on I to the initial value problem that we've already written down. A prime, or x prime equals a x plus f. And it's an initial value problem, so we would have to know the values of x at some times 0, which we'll just call x0. So that would just be a column of initial values, one for each variable.